thanks for watching Edupedia World videos. This is the final video for the 12th class physics syllabus, and in this we'll cover different types of communication systems. Communication is something that dominates our life every single day. Whenever you talk to somebody else, you're basically converting thoughts to language, and that language is being transmitted through sound to another person, and that person is converting that language back into thoughts or ideas. So communication occurs every day, but we'll start from communication of typical things which you would have seen. For example, communication of sound through a telephone, communication of files when you send an email to somebody, communication of pictures, which would be basically a video film which you can also send through the internet or you can see through a television. So every type of communication system has a similar structure, though the details may differ, and first I'd like to draw that structure. So first you have your information source, and finally you'll have somebody who will be the user of information. These two things are not part of the communication system, they are the inputs and the outputs of the communication system. So this would be the user of the information. Say you're saying something and you want that sound to be transmitted to somebody else on the other line of a telephone. So whatever is going to be in between these two things will be the general communication system. So the information source sends what is called a message signal, and the first element of the communication system is called a transmitter. So for example, when you are talking on the phone, sound is being sent from one position to another, but sound, as we've already learned, it consists of pressure waves, and it is quite hard, in fact nobody's done it till now, that you can send pressure waves through hundreds of kilometers or miles without diminishing them in magnitude. So we need to convert those pressure waves into some other form of energy which can be easily communicated or which can easily travel through long distances. So that's what a transmitter does. It converts one type of message signal into another type of message signal which would be easy to transmit over long distances. Then you have the transmitted signal which goes to the channel. So the channel will be whatever transmits it. So if you have long wires which we call telephone cables, then the pressure waves or the sound will be converted to an electrical signal, and that electrical signal will be transmitted through wires, and those wires will be called a channel. Now when the other user gets the electrical signals, they cannot understand the electrical signals for themselves, so they need something to convert those electrical signals back into sound, and that is called the receiver. And the thing that the channel sends to the receiver is called the received signal. And finally, the receiver sends the message signal to the user of the information. Say you wanted to transmit something across lots of televisions, then you would have an information source which would be converted into a type of transmitted signal that can easily be transmitted through long distances without diminishing in magnitude. That would be transmitted through the channel, and then the receiver would take that sort of information signal and convert it into the information signal which the user would want, which would be, for example, audio and video. Now a lot of the times, due to external effects, when the channel is transmitting signal, there is something called noise which interferes. So noise can be, when you talk about sound, noise is what it literally means, but noise can be any form of disturbance which basically changes your signal. So when you have the receiver, it's the receiver's job to cut out all the noise and try to form a proper output message of the input message signal. Now, there are two basic types of communication system or basic modes of communication which fall under this basic category. The first type is called point-to-point, and this type of communication has one transmitter and one receiver between a channel. So a channel has an input of one transmitter and an output of one receiver. This could be, for example, you making a phone call to a friend. Then there's another type of communication mode which is called broadcast. In that you have one transmitter going into the channel, but you may have hundreds, thousands or millions of different receivers. So for example, when a radio station is broadcasting some messages, then anybody who has a receiver or a radio set can actually listen to those messages. So the radio signal is not just going from one person to another person, it is going from one radio station to a wide variety of different devices which can actually interpret those radio waves. So this is the basic structure of a communication system. Let's look at the different types of elements in detail. So the first important element is part of the transmitter but is generally studied differently. It is called the transducer. And basically any device that converts one form of energy to another is a transducer. And basically when you have a telephone that you're making a telephone call, then the pressure waves are converted into an electrical signal, and that electrical signal is transmitted. So the device which would convert pressure variations into variations in current, or a pressure wave into an electrical signal, would be the transducer. Second, you obviously have what I just mentioned, the signal. The signal is basically the information, and generally when transmitted it is contained in electrical form. And when it is contained in electrical form and suitable for transmission, it is called a signal. They can be of two different types. The first is analog and the second is digital. We already know the difference between the two. Digital can only take one of two values, 0 or 1, and it is a binary system that extensively uses digital electronics and employs two levels of signals, 0 corresponding to a low level and 1 corresponding to a high level of voltage. So it can take two values. Analog can actually take many values, and they are essentially single valued functions of time. For example, generally they are taken to be sinusoidal functions. So you could have an electrical current varying with time or a voltage varying with time like this. This is basically a single valued function of time, and it's not like the value is only between 0 and 1 or something. It can take any value between the minimum and the maximum value. Now there's a theorem which you'll learn in mathematics, in higher advanced mathematics, and that is called the Fourier theorem. You don't need to go into the details of that right now. All it basically suggests is that any periodic function, it could be like this, a sinusoidal function, or it could be like this, or it could be anything like this. But any periodic function, that is any function which repeats after a certain time, can ultimately be thought of as a superposition of finitely many or infinitely many sinusoidal functions. So if you take a sinusoidal function like this and a sinusoidal function with, let's say, half the frequency, and a sinusoidal function with double the frequency, and you add them in appropriate combinations, then the sum of them with appropriate weightage to each frequency would ultimately give you either this result or this result. So we can break any type of periodic signal into different sinusoidal functions, and we can also take different combinations of sinusoidal functions to create any form of periodic function. So when you have a signal like this or any complicated periodic function, that can be seen as a sum of many sinusoidal functions of different frequencies taken in different proportions. The third element, which you've already seen, would be noise. It refers to unwanted signals that disturb the transmission and processing of signals, of the message signal we should say, because they are also signals. So when you're converting the message signal to the transmitted signal, or when you're converting the received signal back to the message signal, you can have unwanted disturbances which are generally referred to as noise. Now the element which actually contains the transducer, which we saw in the flow chart, that is called the transmitter. And the transmitter is the device that processes the incoming message signal so that it can be made suitable for transmission, or so that it can be easily transmitted. We've already seen in the chapter on sound waves that when you have sound waves traveling in air, their intensity can actually reduce with space. So it's not very easy to transmit sound waves or pressure waves as they are from one point to another. But you can convert them into electrical signals, and electrical signals can easily be transmitted through wires. Then you have the opposite of the transmitter, which would be the receiver. And it extracts the desired message signals from the received signals. At the channel. What was the channel? The channel was the thing that transmits it from the transmitter to the receiver. The channel would be the wire, or now we can have various wireless communication systems as well. Then we have some properties of the signal itself. One of the property which is attenuation. And attenuation is defined as the loss of strength of a signal while propagating through the medium. Now something like a pressure wave would be highly attenuated when you're sending it over thousands of kilometers, so we can't do that. But electrical signals, even though they are attenuated a little bit, not as much as pressure waves, so they can be transmitted quite reliably. The next, which is the opposite of attenuation and is something we often need to do to be able to transmit the signals from one place to another, is called amplification. The next important definition would be range, and as the name suggests, it is the largest distance between a source and a destination. Up to which generally the signal is received with sufficient strength. Obviously, with a minute strength you can send it to very large distances, but a minute strength will not be of any use if you cannot convert it by the receiver. Then you have an important quantity for communication called the bandwidth. It refers to as the frequency range over which an equipment operates. So bandwidth is generally not just used for communication system. Bandwidth generally refers to a frequency range. So for example, human beings can hear things if the pressure waves are of a frequency from 20 Hz to 20,000 Hz. So that would be the bandwidth of human frequency, of human hearing range. If you are sending something through an electronic circuit, if you're sending something through a channel and it can send something between 2000 Hz and 5000 Hz, that would imply that this equipment has a bandwidth of 3000 Hz, starting at 2000 Hz. Another important term which we'll study a little bit later, which is called modulation. Now, when you're transmitting things, you generally have something called an antenna. I'm sure you would have heard the word before. And an antenna is basically like a simple rod, and it transmits the message signal as well as receives it. In fact, the earlier mobile phones we used to have had an antenna attached to them. We don't have that anymore because it's inside the mobile phone. So generally the rule for an antenna is that the length of the antenna needs to be of the order of the wavelength of the signal being transmitted. So that means the larger the wavelength or the smaller the frequency, the longer the antenna needs to be. And obviously if you look for some frequency ranges, the antenna or the wavelength would be of the order of kilometers, and it's generally not practical to have an antenna of the length of a kilometer. So what we do is, while transmitting information, we would like to have it to be of a high frequency, because high frequency means low wavelength, means smaller length of the antenna. So high frequencies are generally fine, but when you really need to transmit a low frequency signal, what you do is you first convert it to a high frequency signal and then you transmit it, and the receiver converts it back to a low frequency signal. So the transmission and receiving of a high frequency signal would require a smaller antenna, which would be more practical. So the transmitter, at the transmitter, information contained in a low frequency message signal is superimposed on a high frequency wave, which acts as a carrier. So you have a low frequency message signal and it is superimposed on a high frequency carrier wave or a carrier signal. And then the high frequency carrier signal is then easily transmitted, because for that you don't need a very long antenna, you would need a comparatively shorter antenna. There are other reasons as well why we prefer to send high frequency messages over low frequency messages. The attenuation is smaller and other reasons like that. So this process of taking a low frequency message signal and imposing it on a high frequency carrier signal is known as modulation, and it can be of many different types. Amplitude modulation, frequency modulation, or phase modulation. We know there are three aspects of a sinusoidal wave or of any type of wave: the amplitude, the frequency, and the phase. And you can modulate keeping any one of those in mind. In this chapter we'll study mainly amplitude modulation. The abbreviations for those are amplitude modulation or AM, frequency modulation or FM, and phase modulation or PM. Then you have the inverse process, which of course if you modulate a signal you'll need to demodulate as well. So then you have demodulation, which is the process of retrieval of information from the carrier wave. And finally you have something called a repeater, which is a combination of a receiver and transmitter. So this is usually used to extend the range of the communication signal. So if the range is from here to here, then you could have the receiver here, and then you could have another transmitter here and a receiver here, and then you would have the range twice as much, and then this thing would be called the repeater. So you could have several repeaters in line, and that could easily increase the range of communication. Now let's look at a few different ways in which electromagnetic waves, which are the most likely transmitted or received signal, is propagated in nature. So the first type of waves are called ground waves or surface waves. And as we discussed before, the antennas of the receiver or of the transmitter should have a size of the order of the wavelength of the frequency. So the smaller the frequency, the higher the wavelength, the bigger the antenna we need. When you have a standard AM broadcast, the frequencies are generally lower compared to the FM or the TV broadcasts. So amplitude modulated waves are generally transmitted through ground or surface waves. And in that case, you have a lot of ground-based vertical towers which are used as transmitting antennas. You've probably seen them before. They would look something like, I can't draw them properly, but they would be these antenna type towers which you've probably seen in many different locations. And these towers generally transmit ground waves. Those waves, if this is the earth, you would have many towers like this, and waves go from one tower to another, a lot of them being absorbed by the earth, so there's a large attenuation, and these waves glide over the surface of the earth, and they are called ground waves or surface waves. They are generally used for small frequencies, and that's why you need to have really big antennas, because small frequencies means larger wavelengths. They are generally used in amplitude modulated broadcasts. Then you have the other type of propagation, which is called sky waves. Now we've discussed layers of the atmosphere before, and one of the most important layers in the atmosphere is called the ionosphere. When energy from the sun's rays strikes the atmosphere, it generally creates ions in the atmosphere, and that layer is called the ionosphere, and this ionosphere can actually be used to propagate and reflect signals. So you could have signals that would be transmitted by somewhere on the ground, and then those signals would go to the ionosphere, be reflected by the ionosphere, and then you could actually have waves transmitted through a longer distance, because the ionosphere does not have many impurities, it is quite high up, and there is not a large attenuation. So the intensity is not decreased very much. The frequency range in which sky waves are generally used is about 30 to 40 megahertz. So it would look something like this. This is the earth. You would have a transmitter here, and if this part of the atmosphere is the ionosphere, then you would have just rays going like this. Some of them would obviously not be reflected, but a good proportion of them would be reflected back somewhere here where the receiver would be. And this is how, using the reflection of the ionosphere, because it contains positive and negatively charged ions, you could actually transmit waves through longer distances, as opposed to ground waves where waves just glide over the surface. In sky waves, waves are actually reflected back by the ionosphere, and in this case you have lower attenuation. And the third and the most efficient way of transferring waves is by what is known as space waves. Space waves are generally used for a lot of line of sight communication, which is abbreviated as LOS. So unlike what the name suggests, they go right up into space, they actually are waves which travel in straight lines. And since they are waves which travel in straight lines, they spend the minimum amount of time in the air, and so they have the lowest attenuation. A problem with this line of sight communication occurs because of the curvature of the earth. So because the earth is not flat, you generally may or may not have the receiver and the transmitter sharing a line of sight. So let's say this is the transmitter and let's say this is the receiver. I made the transmitter I think a little too big for this figure. So if this is the relative height of the transmitter and the receiver, then you can see that they just barely share a line of sight. If any of these was smaller, then they would not be able to have any wave traveling from one to the other. So whenever you have a transmitter which transmits space waves, you need to have them of minimum height. Now we'll not go into the mathematics of it, but we'll just give you the formula. Let's say this is HR, the height of the receiver. This is HT, the height of the transmitter. This total is the modulation distance dm, which can be broken into two. This is dt, the distance of the top of the transmitter to the horizon, and this is dr, the distance of the top of the receiver to the horizon. All this comes about because of the curvature of the earth, remember that. Then the formula that is generally true is dm, which is the total distance dr plus dt, is equal to root of 2rhr plus root of 2rht. Basically dr is root of 2rhr, dt is root of 2rht, where r is the radius of the earth. Approximately 6400 kilometers. So these are the processes by which you can actually transfer waves from one point to another. The three processes which we studied now, they all come under the channel, because the channel is what transmits the information signal after being converted to the transmitted signal from the transmitter to the receiver. The channel has the greatest length. So you could have ground waves which travel over the surface of the ground and they generally get highly absorbed by the earth's surface. You could have sky waves which are reflected by the ionosphere, and then you could have space waves which generally travel in straight lines and therefore have the lowest attenuation. Now we'll discuss modulation in detail in the next video, and in this chapter we'll only be discussing specifically AM or amplitude modulated waves. Thank you.